In this video, we're going to introduce bits and describe how they can be combined to produce binary numbers. Before we get started, let's make clear that there's a distinction between the number and its representation. The number, such as 7, is a very abstract quantity. Here we have 7 apples. 7 is not a property of any individual apple, nor is 7 a thing in itself, but it's something that we use to describe the size of a set. In this case, we have a set of 7 apples. We can represent that number in various ways. Here we see several ways to represent the number 7. In decimal, which is of course convenient for arithmetic computations like addition and subtraction. We can spell it out. This is the Roman numeral 7. And here we have the representation of 7 as a binary number. We'll describe more about this in a second. And finally, we have the representation of the number 7 as 7 dots. All of these are representations of the number 7, but none of them is the number 7 itself. And it's important to make clear that distinction. We're going to be talking about how to represent numbers and how to perform arithmetical operations on those representations. We'd like to take our representation of a number and store it in a computer memory. So let's begin with the smallest amount of computer memory that is imaginable. And this is a 1-bit memory cell. I've tried to indicate the memory cell with a rectangle here. And the idea is that this rectangle, this cell, is big enough to hold either a 0 or a 1, but not both. So it can have exactly one of 2 values in it. The 2 values are the 2 bits 0 and 1, and at any one time this box will contain either a 0 or a 1, but not both. We can equate the 0 bit with false and the 1 bit with true, and this is oftentimes useful if we want to remember whether a particular thing is true or false. Or we can associate the bit with yes or no, and the correspondence there is that 0 corresponds to no and 1 corresponds to yes. But now we're talking about what the bit represents. With only 1 bit of memory, we can basically represent either true or false, or yes or no, or something with only 2 values. To represent something more complex, like a number, we need to have more bits. Here I've drawn 8-bit cells, all put next to each other, and together we call these a byte. Every byte contains 8 bits. So in this picture we have a memory that is capable of containing 8 bits at once. It's not a very big memory, but it's 8 times larger than this memory up here. And at any one time it will hold 8 bits. Here are some examples of the kinds of patterns it can hold. So our short little memory here can hold 0110, 11001, or maybe it holds something different like 10101100. At any one time it's holding exactly 8 bits. Every cell is either a 0 or a 1. I've drawn it blank here, but in reality a computer memory always contains either a 0 or a 1. Now there are lots of different values that we could put into these 8 bits, into this 1-byte memory. And the next thing we want to talk about is how many different combinations are there? How many different bit values can this 8-bit cell hold? To analyze how many different possible values we can get into our 8-bit memory, let's start and look at just a 1-bit memory cell. Using only 0 and 1, there are only 2 possible values that we can store in that 1-bit memory cell. Now what if we had 2 bits of memory? Well, I've listed out all the combinations in this column that we could possibly store in a 2-bit memory. 00, 01, 10, 11. So if we have a memory that is only 2 bits in size, at any point in time it will contain exactly one of these 4 values. But let's say we have 3 bits of memory and we want to represent more combinations. Well, we can add a bit to the left. Imagine adding a bit to the left, and that bit could either be a 0 or a 1. So here I've listed our combinations 0, 0, 0, 1, 1, 0, 1, 1, all with a 0 in front. And here I've listed them again 0, 0, 0, 1, 1, 0, 1, 1, all with a 1 in front. So notice how the number of values doubled. Okay, here we had 4 possible values, and now we have 8. By adding an extra bit, we double the number of possibilities. Now, here I'm doing the same thing again. I'm assuming that we now have 4 bits of memory. And I list all of these 8 combinations here, from here to here, with a 0 in front, and then I list them again with a 1 in front. So we start with 2 possible values with a 1-bit memory, and we double it to 4. And then we double it to 8. And then we double it to 16 different values. Now let's look at these values a little bit more carefully. We'll call the bit on the right side the least significant bit, and the one on the left end the most significant bit. So let's look at the least significant bit. Notice how it changes 0, 1, 0, 1, 0, 1, and we pick that up from the fact that we repeat this here like that over and over. And then we have the second bit right here. It goes 0, 0, 1, 1, 0, 0, 1, 1, and we're picking that up from here. And then the third bit, there are 4 zeros, 4 ones, 4 zeros, 4 ones, and finally 8 zeros and 8 ones. And the pattern would continue if we had 5 bits or 6 bits or more bits. Also notice that the first value is all zeros and the last value is all ones. The next thing we'd like to do is associate with each one of these possible bit values a number. And so let's start with 4 bits. Here I've shown all the possible combinations again, just like on the last slide, of all of 4 bits, starting with 0, 0, 0, 0 and ending in 1, 1, 1, 1. And I've associated with each one of these a number. And I've represented the number here in decimal, but that's just because I like decimal and it's something we can all understand easily. But remember that the concept is that this is a number, and I might have represented it in using Roman numerals or some other way. But decimal is the system that we are all familiar with. So, and I've listed the binary numbers in exactly the order that I've generated them. And I've listed the numbers that they represent in order as well. So notice that the binary value of all zeros corresponds to 0. And the binary value of all zeros with a 1 in the least significant position corresponds to 1. And then all the way up at the top, the greatest value is associated with 1, 1, 1, 1. So with this system, I can represent any number between 0 and 15 with 4 bits. So now we see how numbers can be represented in a computer memory. If we have a 4-bit memory, we can store any number between 0 and 15. We have 16 possible combinations of bit values, and we can associate with each one of those combinations a number according to this scheme here. I also want to talk about how we can go from one number to the very next number. So let's just take, for example, 6. If we want to increment it to 7, well, if it contains a 0 in the least significant bit, we just change that to a 1. And that works for any of the even numbers. For example, if we want to increment 0010 to the next number, we just change the least significant 0 to a 1, and we go from 2 to 3, or from 8 to 9, or from 14 to 15. Now, if the least significant number is a 1, as in 5, then we change it back to a 0, but we change the next 0 to a 1. So here we're changing this 1 to a 0, and we move over and we change this 0 to a 1. If it's a 0, that works, like incrementing from 5 to 6. Let's look at 3. Here we change the 1 to a 0, and we go over here to change this 0 to a 1, but it's not a 0. It's also a 1, so we change it to a 0, and we keep going until we find a 0, and then we change that to a 1. So whenever we have a sequence of 1s on the right-hand side, we change them all to zeros until we hit a 0, and we change that to a 1. Here's another example. This has a 1 in the least significant bit, so we change it to a 0. We move over, we change that 1 to a 0, and we keep doing that until we hit a 0. Oh, the next place is a 0, so we change that to a 1, and we stop there. So that's the procedure for incrementing a binary number from one value to the next value. Now notice if we try to increment 15, we start changing our 1s to 0. We never hit a 0, and so it doesn't work with 15. These are the numbers that we can represent with only 4 bits, only 16 different values from 0 to 15. With more bits, the pattern is exactly the same, but we have many more combinations. So here I've shown 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. And with this many bits, we have a total of 256 possible combinations. I'm not listing them all out because there are a lot, there are too many for this slide, but they start at 0, and since there are 256 different binary values with 8 bits, we have a top number of 255, which is 1 less. So here our largest number is 255, and here our largest number is 15 because we have 16 total values. With 32 bits, we have a lot more combinations, and of course the table would be impossibly large, so I'm not going to list all these possible bit values, but they start off the same, all zeros, 1, 1, 0, 0, 1, 1, and so on, just like with 8 bits and 4 bits, and they keep going until we get a value of all 1s. In the case of 32 bits, we have 32 1-bits, and that corresponds to a number of 4,294,967,295. So the total number of values we have is just a bit over 4 billion different values.